So the last talk is on smart urban signal networks. It's an initial application of a SURTRAC adaptive traffic signal control system, and it's going to be presented by Stephen Smith and the joint work with his team as several students at Carnegie Mellon.
Okay. Perfect. This is joint work with Greg Barlow, Xiaofeng Zi, and Zach Rubenstein, which represent my traffic group at CMU. We've been working for the last several years now on the problem of real-time adaptive control, traffic signal control, for urban environments, sort of an area that traditionally has been said it's not really doable, and people have shied away from it, and we're trying to move the other direction. Last year's ICAPS, I presented a decentralized algorithm that we developed and evaluated in simulation, got very nice results. Since that time, over the last year, we've actually carried out a deployment implemented the system and deployed it on a traffic signal network in the East Liberty region of Pittsburgh. It's a grid network of 9 signals. So that's the work I'm going to talk about today. So real quickly, I'll say a few words about the traffic control problem just to set context. I'll review the SURTRAC approach. SURTRAC is the name of the system that we've evolved. Scalable urban traffic control. Then I'll talk about the pilot implementation of the system and results, and tell you a little bit about what we're currently working on. So the problem we're focused on is congestion. It's a worldwide problem. I've given some statistics here about costs in the U.S., taken from 2011 annual mobility study of urban areas. So, you know, the numbers are pretty big. They estimate the cost in time and fuel to commuters overall over the country, in the urban regions, $101 billion. Also, lots of emissions pouring into the environment. Another study says that we spend 40% of our time on surface streets in urban areas idling, sitting there waiting in traffic. So there's definitely a problem. If one thinks about how to reduce congestion, the sort of traditional answer is to add more capacity, build roads, widen roads, accommodate more vehicles. In urban areas, in particular, that's just not possible. There are land use issues. There's limited space. Area like Pittsburgh, for example, is geographically constrained with mountains and tunnels, and you just can't build your way out of it. So you need to look for other ways. Mass transit is and sort of pushing people towards use of mass transit is certainly a goal. Another approach, the one we're pursuing, is to try to improve traffic flow. So our mantra is that smarter traffic signals can help. It is sort of generally agreed upon that on surface streets, traffic control improvements offer the biggest payoff. Although they're not really in wide use yet, adaptive traffic signal control systems are generally believed to hold the most promise for improvement. So to give a little context, what you're looking at here is the actual kind of plan that we would like to come up with and continually modify traffic signal plans. In the left corner there is an intersection, and I've labeled different traffic flows through the intersection. Actually, these are standard labels. And what typically is done is compatible flows are grouped into what are called movement phases. And then a movement phase, a signal timing plan, is just a sequence of phases with some duration, some amount of green time allocated to each phase. So you can see there in the middle of the screen just an example signal plan, and you can see that it repeats, and that's quite common. You'll run in a cycle, and then the cycle will just repeat. So where the variability comes in is the duration of the green time that's allocated to different phases, and you can also think about skipping phases. If there's nobody to turn left, you can skip that phase. So conventional signal systems build these signal timing plans offline. So they're pre-programmed. Sometimes they incorporate simple actuation. If you've ever driven up to a traffic light and there's no traffic there, and maybe there's a sensor in the road that'll sense your vehicle, give you a little green time, and then put you back on the main. That's the notion of simple actuation. You can use several pre-programmed plans for different times of day. That's often used. But the main point is that they're pre-programmed, fixed, and they don't change over time. They have to be manually retimed. Adaptive signal systems, on the other hand, sense current traffic flows that are coming at the intersection and dynamically will adjust the signal timing plans in real time or in some form of real time. So adaptive traffic signal systems aren't new. There are multiple examples of systems. It's a problem that's been studied in the traffic engineering community for many years. Centralized systems have had the most success. I've listed a few there. One limiting factor with a lot of these systems, since by nature they're pulling all sensed information back to sort of a common location and cogitating on it and then making a decision to change the plan, is that plans tend to change on cycles of 5 to 10 to 15 minutes. So it's not what you'd call real time, and you could be limited in your response, in your ability to respond to immediately to situations, traffic accidents or vehicle parked in a lane unloading, so on. There are other approaches that I've called here online intersection planning approaches that do focus on the real-time problem, and these also extend very naturally to the network level, to the traffic network level. In fact, the SURTRAC system that we're proposing takes this form. What has historically been the problem with these kinds of techniques is that the computational requirements really restrict the planning horizon that of the intersection planner and or the timing, the precision of the timing, and that all limits effectiveness. I'll come back to it in a minute, but one of the innovations of our approach is a formulation of the problem that allows us to solve it very, very quickly. If you have a single dominant flow, say an arterial situation, then several contemporary systems will make use of a shared global timing plan, and then the adaptive problem just becomes one of managing the simpler problem of managing the traffic on the side streets. We're interested in urban environments that have more of a grid character, and there you can't presume a particular dominant flow. There are multiple flows, they're typically conflicting, and they'll tend to evolve over the day. SURTRAC is a decentralized. We take a totally decentralized approach. Each intersection controls its local traffic, sees the traffic coming at it, builds a plan to move the traffic through the intersection in the most efficient manner. So let's see if I can. We're currently using cameras, but what happens is we're sensing traffic conditions are extracted from the sensor data streams in real time. They go into the intersection scheduler. The scheduler then will build a phase schedule that optimizes the flow through that intersection, the traffic it's seeing locally. And then it uses that schedule to send commands to the actual controller, the hardware device that actually drives the traffic lights. So it tells it when to stay in this phase, move to another phase, etc. Whenever it builds a new schedule or timing plan, it communicates what it expects to be the outflows to its neighboring intersections. They're doing the same thing. They're computing the schedule. Now they have, in addition to the traffic that they can see with their sensors, they have now sort of an advanced projection of what's coming down the pike before, so they have a bigger horizon to plan against. And then this whole process at each intersection runs on a rolling horizon, so the scheduling cycle is repeated every as frequently as once a second. So there are kind of two key technical ideas that I talked about last year that really sort of underlie the approach. The first is a formulation of the problem, the intersection control problem, the individual intersection control problem, as a single machine scheduling problem. So we use an aggregate representation of traffic flows as sequences of queues and clusters, and those give us the input jobs to the intersection machine, if you want to think of it that way. Then we build a schedule to sort of move those jobs through, treating them as non-preemptive. And then on the second idea then at the basic level is just to communicate schedules, these planned outflows downstream neighbors to just give visibility of future input jobs. That basically what we're doing there is making an optimistic assumption that the schedule, the plan will execute as expected, and if it does, everything will be perfectly coordinated. Of course, it doesn't always happen that way. You have vehicles coming from side streets, et cetera. So on top of that basic communication protocol, we layer mechanisms for coping with miscoordinated situations, spillback, for example, that account for the fact or specific kinds of situations where there may be miscoordination. I have 10 minutes. Huh? Okay. I'll just give you a little more detail about these ideas. So, first, with respect to the formulation of the problem, here's a sort of a sensor stream or a stream of values that are coming from a detector intersection. We cluster these input vehicle streams in two ways. One, we group vehicles in similar proximity into clusters, what you might think of as platoons, and then we also form what we call anticipated queues. Basically, a set of vehicles that may be stopped at an intersection waiting for a green, along with those that are expected to join that queue before the queue can clear. So that gives us a scheduling problem. Here I have two different phases, different directions, and then to build a schedule is simply generate a sequence of clusters. Then once I have a schedule, I can turn that into a planned signal sequence by adding the various constraints on the yellow and all red time and so forth. So then the scheduling problem is just to minimize the cumulative delay of all jobs subject to the timing constraints for safety, that's the yellow time, and fairness, which are minimum and maximum times on a given phase, so nobody gets starved out. Okay, we use a forward dynamic search. I'm not going to spend too much time with this. The key idea here is that the complexity of the problem is turned from one that depends on the planning horizon, the size of the planning horizon, to one that depends on the number of phases and clusters, which is typically much smaller number. And in our experiments, we've shown that we've been able to solve this in comparison with state-of-the-art techniques, 2 to 4 orders of magnitude faster. I said our basic coordination is to communicate to neighbors. We have a mechanism for detecting and reacting to spillback, the phenomenon where you use the capacity of a road segment and your vehicles start extending back into the intersection. So we have a policy for recognizing when that might be happening. Another second form of coordination is what I've called here network-driven actuated control. There's a trade-off with adaptive. The longer you can make the maximum times, the more flexibility you have to move traffic. But On the downside of that is you're potentially starving out the few that aren't in the big flows. So one other mechanism we use here is we also communicate, each intersection will communicate when it moves into a new phase, so that neighboring intersections can recognize that they're in a cross phase, and if that's the case, they can go red, service either pedestrians or cross traffic, and get back without really stalling that flow, because it's going to have to stop anyway. Okay, so we cooperation with the city of Pittsburgh, we found a location to carry out an initial deployment. This one was attractive. This is an evolving area. Fairly recently, a Target department store was put in, and along with that, the 8 blue circled intersections were reconstructed and outfitted with cameras. So it was a very low-cost way of trying out an initial deployment. We actually added detection and upgraded a 9th intersection to give more of a grid. There are really 3 flows through this intersection, or I'm sorry, through this network. There's the Penn Circle that's looping this way. There's Penn Avenue that's moving east-west. And then there's a north-south moving through from a neighboring Shadyside neighborhood. Here's how our system looks in the field. You probably maybe don't notice it, but at every intersection that has a traffic light, you'll find one of these boxes. We essentially put a new a new processor in each intersection. That's what runs our system. I've called the SURTRAC processor there. That is connected then to the Trafficon camera video boards and the controller, and really that manages it. A few words about the system implementation. We operate by overriding the existing timing plans that are there, but we do that in a way that allows the system to revert. That was a big problem when we started. We've in fact never had to do that. But the system also tolerates loss of communication with its neighbors. So if a failure in the network is detected, a given intersection will automatically, after some amount of time, shift to just using moving average flow forecasting data, so that there's graceful degradation if you have network problems. And the architecture is designed to operate with different equipment. One of the problems that we immediately, when moving from simulation to the real world, was the uncertainty associated with sensors. So there are several sources of sensing uncertainty. You have detector areas where the vehicles simply don't drive over the zones that you've mapped out in the cameras. You also have unexpected disruptions, like vehicles stopping to unload, or a bus stopping at a bus stop mid-block and blocking the traffic. So the net effect of all this uncertainty is inaccurate queue length estimation. That's not necessarily a problem with overestimation, but it certainly is with underestimation. So we have developed a couple mechanisms for triangulating between different sources of information to correct that. I'll refer to you to the paper for that. Here's a let's see if I can get it going. Here's just a shot of SURTRAC in action. This is an afternoon. We took a video. This is the main intersection in the pilot. It's sped up 4 or 8 times, just so you can kind of get an idea of the flows before on the front, after on the right, we just turned the system off for a while, took video, turned it on for a while, and took video. So I think if you see the gestalt, you can kind of see that there's quite an improvement. We did do a formal evaluation, a before and after drive study through the performance area. What we did was we selected the 12 highest volume routes, and essentially conducted multiple drive-throughs with vehicles through these 12 routes in 4 different periods of the day: AM rush, mid-period, PM rush, and evening. We had GPS devices and just traced our paths, and from that we can extract transportation efficiency and emissions data. What we did was compare against the pre-existing timing system, which was actually coordinated, actuated timing plans that were generated originally by a tool called Synchro. Synchro is a state-of-the-practice optimization tool for offline design of signal plans. That was done, and those signal plans were enforced for the AM and PM rush. In other periods, they were just running in what's called free mode, which just dedicates you to a major artery and then uses the cameras to recognize when somebody's waiting at a stop and gives them service. These plans were built about, I'd say, within a year of our test, which is important to know because signal plans degrade over time, and typically they say every 2-3 years you have to retime them. Nobody ever does because nobody has the money to do it, but they do tend to degrade. So these were fairly recent plans that we were running against, and the results are averages of 3 runs in each period under each condition. We did a 4th run for the PM rush on Friday, just because in our experience implementing, that seemed to be the busiest time of all. So here are just some summary results, and you can see we got very nice performance. This is I've listed the performance. These numbers are aggregated by volumes on the routes, and you can see the different periods of the day. But overall, we've got 25% reduction in average travel time, 34% improvement in speed, 40% drop in wait time. We didn't have emissions detectors, but using a model of fuel consumption, we projected that we reduced emissions in the area by over 21%. Actually, the organization that funded us we were really funded as part of a BREATHE initiative that a local foundation was. So it was really improving the quality of the air that was their motivation for giving us the money to do this. We've been running continuously here now for about a year, since last June. We've gotten funding to expand the test site in a couple different ways. So we're currently extending 9 more traffic signals moving eastward from the traffic site to it's a tech area where Google Pittsburgh is and all of that. That should be done within the next month. Okay, I'm almost done here. And then in the later part of this year, next year, we'll move in the other direction. We expect to be doing a scalability test of 45 intersections by the end of 2014. So some of the research directions that we're currently working on, or things we're interested in. One area is this notion of optimization for environmental impact. Right now, we're minimizing cumulative delay. We're really focusing on vehicle flows. And conventional argument, which I, to some extent, believe, you can see by the numbers, says that if you optimize traffic flows, you'll minimize environmental impact also. But I do think that there are opportunities. If I was thinking purely about improving the air quality, maybe I'd want to focus more on minimizing stops. You should see the buses in Pittsburgh when they start up every time, rather than the travel time. So there might be some trade-offs that you think of. So we're interested in doing that. Since we're in urban environments, we're very much interested in multimodal traffic management, sort of the integrated optimization of all kinds of flows, giving attention to mass transit, pedestrians, bicycles, and so forth, in addition to vehicles. One of the things we're currently doing is looking at opportunities for recognizing buses and taking that, once recognizing buses, taking that into account. In the longer term, what we're really interested in is monitoring and shaping traffic flows. So as part of that second phase of implementation, they'll also be installing DSRC radios, which are the sort of the in-car radios that the connected vehicle community is working with. So we're very interested in connecting as vehicles start to talk to the infrastructure, being able to take advantage of that, and if they're willing to tell us our destination, sort of solving that larger optimization problem. So, thank you.